Okay, so we're recording now, and we can look at the presentation.
All right, so hello everyone. Welcome to our third virtual SI meeting. Thank you for coming. Today we will mostly be talking about energy and work and the associated things with that. So to start us off, while we're still waiting for everyone to come in, we'll go ahead and go over some of our formulas, right? So Freya, if you want to go to the whiteboard.
Yes, so I will go over the whiteboard, sharing. Okay, so we're going over energy, conservation of energy and work specifically. So what equations do you think we need to remember, Josh?
Well, we have one equation for work, which involves the dot product, which that would be the work is equal to the magnitude of any given force multiplied by the magnitude of its displacement. And that is also multiplied by the cosine of the angle between those two vectors.
Right, so that's one equation for work. Another way we can look at it is in terms of energy. So we know that work is equal to the change in kinetic energy, or kinetic energy final minus initial. Okay. Are there any other equations that we need to remember?
Just a second, Freya. If you give me a minute. Oh, it's okay.
Yeah. Okay, so we have these equations for work. We also know that kinetic energy is equal to 1/2 mv squared. And potential energy is equal to mgh. So those are the equations that we can use to calculate kinetic or potential energy, which is useful if we're using it in an equation for work. Okay. So those are some of the equations that we're going to be using today in our examples. And so it's a good idea to keep those in mind. And yeah. So give everybody another minute or two to see if anybody else joins. I know there were some issues with the attendance sheet, and then we'll get started on our examples.
Hey, come back. Sorry about that. I had someone have to come pick up their stuff in the room I was in.
Okay. So, Josh, can you think of any more examples to add to these, or do you think that's good?
Well, I mean, there is Newton's second law, which is always useful. Probably good to have that one on your mind. Most people have that memorized by this point, but that would just be the sum of the force vectors is equal to the mass times the acceleration vector.
Okay, so that's another good equation to keep in mind.
Oh, and then there's also the conservation of energy one that he used, which was kinetic energy 1 plus potential energy 1 is equal to kinetic energy 1 plus potential energy 2.
Right, because energy initial is equal to energy final.
Yeah, so what that means is that, you know, all of the energy in the beginning is going to be constant with what we have at any other given point, because energy cannot be created or destroyed.
Okay, So now that we have that, I think we can get started on our example. Okay, so here we have example 1. A 2-kilogram box is released from rest at the top of a frictionless ramp. After sliding down the ramp, the box slides across the surface with friction coefficient mu k equals 0.50. How far does the box slide on the rough surface? And there's going to be a couple of different ways to solve this, so we're going to do it 2 different ways and then compare and see which one is easier. So what's one way that you think we can solve this, Josh?
Well, I'm kind of cheating, but looking at the slide, it says that you can solve it using energy formula.
Right, so we can solve this using energy. So why don't we do that? I'll open up the whiteboard. Okay, so we have a ramp that has a height h equals 0.25 meters. And it goes onto a rough a surface with friction after it goes down that ramp. We want to know how far along that surface it will slide. And we know that the box is 2 kilograms and that the friction coefficient is 0.50.
So just to be clear, where is there friction and where is there not friction in this example?
So we have friction along the horizontal and no friction along the ramp.
Okay.
Okay. So using our ideas of conservation of energy, why don't we start by looking at how much energy we have at the beginning of this problem when the box is first released. So at the top of this ramp, does the box have kinetic energy?
Well, while it is at rest, by definition, it is not moving. Therefore, it cannot have kinetic energy, which must mean that all of the energy that it has is going to be potential energy due to gravity.
Right, and as we remember, our potential energy equation is equal to mgh. Therefore, our potential energy is equal to the mass of 2 kilograms times our gravity, which is 9.80, times height, which is 0.25, which gives us potential energy, or total energy, because that's all that's there, of 4.9 joules at the beginning of the problem. Okay. So now that we know how much energy is at the beginning of the problem, what's the next step you think we need to look at?
Well, as it's sliding down the ramp before it reaches the friction horizontal surface, it would technically still have potential energy, but it would also have kinetic energy, right? However, I don't know if we necessarily need to take that into account, because what we're asking to find is how far it travels along the horizontal surface. So I think that the next step in our equation, or at least in our solution to this problem, would be to look at it at the next critical point, which is when it reaches the rough horizontal surface.
Right, so at the bottom of the ramp, this area here. So at that point, if we're considering that to be ground level, so we're considering that to be a height of 0, do we have any potential energy at that point?
No, we would not, because if you multiply 0 by mg, which is our equation for potential energy and gravity, you just get 0. So there can't be any potential energy from gravity.
Okay. So as we know that all of the potential energy has been converted to kinetic energy, we can say that the kinetic energy at that point at the bottom of the ramp is also equal to 4.9 joules.
How do we know that it is all kinetic energy?
Well, if we're looking at this problem, we have the option of kinetic or potential energy. And if we're treating that as if it's ground level, because we've had a height change of 0.25 meters, we can treat that as 0, which would give us no potential energy, which would mean that we have only kinetic. We can get this using our conservation of energy equation.
Right, the PE1 plus KE1 equals PE2 plus KE2.
Right. So PE1 plus KE1 equals PE2 plus KE2. And as we have no kinetic energy. Right, so we have no kinetic energy initially and no potential energy at that second part of the problem. We can say that PE1 is equal to KE2.
Okay.
So that's how we're able to conclude that the kinetic energy at the bottom of the ramp is equal to the potential energy at the top. So right before it hits that rough patch, it has 4.9 joules of kinetic energy. Okay, so from that step, we still need to figure out how far it goes along the rough patch. So we know that work is equal to kinetic energy final minus kinetic energy initial. So at that point, when the box stops sliding across the surface, does it have any kinetic energy?
You're asking when it stops?
When it stops.
Right, so yeah, when it stops, once it's reached its maximum distance on the horizontal surface, it is not moving anymore. So it has 0 kinetic energy.
Right. So then we can say that work is equal to the kinetic energy, is equal to the negative kinetic energy on the rough surface. So that allows us to see how much work is done as the box is sliding across that surface until it stops. And then as the other equation for work that we know is that it is force times displacement. So which force are we looking at in terms of this problem?
Well, we want to calculate the work, and since work involves the cosine term, any forces perpendicular to the motion would just have a work of 0. So that would get rid of both the normal force and the force from gravity. The only force that we really need to worry about in this instance would be the force from friction.
Okay. So then all we need to look at in terms of forces for work on this box is friction. And friction is equal to mu k times the normal force. And as it's on a horizontal surface, what is the normal force equal to?
It would just be equal to the gravity, the force due to gravity.
Yeah, mg. So we can say that that is equal to 0.50 times the mass of the box, which is 2 kilograms, times 9.80, which gives us 9.80 newtons. Okay, so now we know that work is equal to kinetic energy, which is 4.9 joules, and that the work is equal to the force times the displacement, so we get 9.80 newtons times some displacement s. And as we know that they are parallel forces, friction and the friction is parallel to the displacement, we know that cosine theta will just equal 1. So we are left with 4.9 joules equals 9.80 newtons times the displacement. which if we rearrange, gives us a displacement of 0.50 meters. Okay, anything to add to that, Josh?
I think it's good. I mean, I think one thing that might be a bit confusing is we calculated that the work was a negative kinetic energy, which would be negative 4.9 joules, right? But then when we were here, we just write it as positive 4.9 joules. I was wondering if you could elaborate more on why that is.
So our frictional force and our displacement would actually be in opposite directions. So you have displacement is going in the positive direction and frictional force is going to be opposing it. So technically the angle between them isn't actually 0 degrees, it's 180 degrees. And the cosine of 180 degrees is -1. So -1 times -1 would give you a -9.80, and you'd be able to cancel the negatives on both sides.
Okay, that makes sense.
Okay. So if there aren't any other questions about how we got to this point, we can move on to the second way of solving it. Okay, I'm gonna clear the whiteboard then. So what is the second way that we're gonna solve it, Josh?
Well, we could utilize Newton's second law to use forces and kinematics to solve how far it will go.
Right. So from that first problem, just taking information from there, we agreed that kinetic energy at the bottom of that ramp was equal to 4.9 joules. And we know that kinetic energy is equal to 1/2 mv squared. So using this, we would be able to calculate our velocity, which would bring us back to our kinematics equations. So if we set this up, we have 4.9 joules equals 1/2 times mass 2 kilograms times a velocity squared. And when you put that into your calculator, you get that the velocity at the bottom of that ramp is 4.9 meters per second. Is root 4.9 meters per second. So that gives you your velocity at the bottom of the ramp. So if we're looking at a horizontal surface with friction, I'm going to have to ask you guys not to draw on the whiteboard because we're using this for demonstration purposes. Okay, so V at the beginning is root 4.9. We know that at the end when it stops, velocity is going to be equal to 0. And we want to know what the distance is between when it starts and when it stops. So using our kinematics equations, what's another variable that we're going to need to calculate this?
We don't need time, which means that narrows down our choices for the equations. And I believe the best one that we could use would be the velocity squared is equal to the initial velocity squared plus 2 times the acceleration times displacement. However, we don't know the acceleration or the displacement, but we're trying to find the displacement. So that means we need to make sure that we can figure out the acceleration before we can go any farther.
Right. So acceleration, and then this brings it back to what you were saying earlier about using our Newton's law equation. So we know that the sum of all of our forces is equal to mass times acceleration. And what forces are we looking at? We reached the same conclusion in the last problem. What is the only force we're looking at?
Right, all the forces balance each other except for friction. So the net force would just be the friction force.
Right, and we said that that frictional force was equal to mu k mg, and that is equal to mass times acceleration. So the mass cancels out. Acceleration is equal to mu kg, which is equal to 0.5 times 9.80. So acceleration is equal to 4.9 meters per second squared. Okay. Now we have V initial, we have V final, and we have acceleration, and we're solving for displacement. So going back to my kinematics equations, I'm thinking that the equation I'm going to want to use is V squared equals V initial squared plus 2a delta x. As this has all of the variables that I want to use in there, but it doesn't have time in it. That's the only equation without time, which is something I don't have. So plugging in for that, we get 4.9 meters per second. Or sorry, 0 meters per second, because that's final, squared equals root 4.9 meters per second squared plus 2 times 4.9 meters per second squared.
Quick question, Freya.
Yeah.
Since the acceleration is in the same direction as the net force, and the friction force is actually opposite direction of movement, should the acceleration be positive or negative?
The acceleration should be negative. That's a good point. Our frictional force here should have been negative, which would have led to a negative acceleration. That's why it's a good idea to keep track of your signs throughout the problem, which will give us a negative here. And yes, that will make a big difference in your answer. So now that we have the problem set up, we have all of our known values plugged in and just one variable left. You can rearrange and solve that. And that will give you a delta x value of 0.5 meters, the same value that we got for the previous problem, for the previous example. So no matter which way you solve it, whether you solve it through kinematics or through energy, as long as you do your math correctly, you should end up with the same answer. Okay. Anything to add to that, Josh?
Which one did you think was easier?
So personally, I think that the energy problem was easier. I didn't have to solve for velocity or solve for acceleration as a separate thing. I was just able to take my initial energy and compare that to what I would have at the end. That seems like it took a lot less work. What did you think?
Yeah, I think that makes sense. I think in general, that's the way physics works. Physics is all interconnected. And so there will be multiple ways to solve every problem. But, as students, our job is to figure out which one would be most easy to do. And that way we can, if we have a question like that on the test, we're able to save time and do it the easiest way rather than spending the extra 5-10 minutes solving it with kinematics. So, yeah.
Okay, sounds good. So unless there's any questions about this problem, I'm going to move on. Okay, clear the whiteboard.
So we're moving on to our next example. Freya, if you want to share the slides. So this example says is that we have a box of mass m, which is a round square, and it is being held h meters above the ground. A spring of natural length L is located directly below it. What is its speed when it reaches the spring? What is the maximum distance that the spring compresses? And what maximum height does the box reach after bouncing off of the spring? And we have our givens here. Our mass is 5 kilograms. Our height is 8 meters. We have a spring constant, which is a constant of elasticity for this given spring, which is 1,000 newtons per meter. And we have the natural length of the spring when it's not compressed or stretched at all, and that is 1 meter. So I think a good idea before we get into the numerical aspect of this problem would be to look at it conceptually, so you get an understanding of what's happening. So I don't think I can write on it currently, but at the initial position, when it's just the box is just sitting up there. Thank you, Freya. When the box is being held at rest at 8 meters above the ground, there is only one kind of energy in play there. Which one is that, Freya?
Potential energy. It's not moving initially, so it couldn't have kinetic.
Right, it's just the potential energy due to the gravity. However, as it starts to fall, it gains kinetic energy and loses potential energy. But the sum of those has to total to the original just potential energy. Then right when it hits the spring, that is when we introduce the new kind of potential energy that we learned about in class recently, which is elastic potential energy when as the spring compresses. So, however, it doesn't just hit it and stop, it's still moving, right? So not only would there be potential energy from the spring and potential energy from gravity, but there also would be kinetic energy as it's still pushing down on the spring. That's the most confusing part, because all three of the energies are at play. Then once it reaches its maximum compression point, as the second question in this example is asking, it stops moving, which means the kinetic energy goes away, and then it launches it back upwards, and we go backwards through that cycle of energy. So we go the same steps, but in the opposite direction. So then we have just potential and kinetic again, and we get back to just potential. So we're introducing, well, not introducing it, but kind of going over a more complex scenario involving energy, where we'll still use our energy conservation concepts to solve this one. So Freya, you want to go ahead and get started with the math?
Yep. So I'll share the whiteboard. Okay. So we have the box, which is above a spring. And okay, we know that the box is 8 meters above the ground. We know that the spring, when not compressed, is 1 meter long. And we know that the box is 5 kilograms. And that K, the constant of the spring, is equal to 1,000 newtons.
1,000 newtons?
Is it 1,000? Just equal to 1,000?
So it'd be 1,000 newtons per meter, would it not?
Newtons per meter, yeah, that's
I don't
correct.
even get a build-up of meters.
Okay, so 1,000 newtons per meter. Okay. So, and the problem was asking for 3 things. So let's start with the first part of the problem. What is its speed when it reaches the spring? So similar to the last problem, I'm thinking that we would want to start by looking at how much energy it has to begin with, which would be at its initial point. And what kind of energy did you say it had at its initial point, Josh?
Just potential energy due to gravity.
Right. So its energy when it's first dropped is just potential energy equals mgh, which is equal to 5 times 9.80 times 8, which gives us 392 joules. So at the very initial point when it's first released, it has 392 joules of energy. And when it's dropped, that will be converted into kinetic energy, although it will have some potential energy still. Okay. Given that we want to solve for speed, what do you think our next step would be, Josh?
We would need to transfer it. Well, it's asking for the speed right when it reaches the spring. So that would be when it's just potential energy and kinetic energy.
Okay. So at that point, we have potential energy plus kinetic energy, which would be mgh plus 1/2 mv squared. And what would that all be equal to?
Well, it would have, by the conservation of energy, it would have to sum to 392 joules still, because you cannot lose or gain energy in our system.
Exactly. So all of the energy must be equal to that potential plus the kinetic. Okay, so using that, we can plug in our values. We have 5 times 9.80 times, what would the height be when it reaches the spring?
Well, it would be the initial height minus the natural length of the spring. So it would be 8 minus 1. So, or it would just be, no, it wouldn't be minus it. Sorry, I said that wrong. It would just be the natural length of the spring because it hasn't started to compress it yet. So it would just be 1 meter.
Right. So when it first reaches the height of the spring, we know it'll be at 1 meter. And we know that we have 1/2, again, 5 kilograms. And velocity is what we're solving for. And that is all equal to 392 joules. So now we're left with just one unknown variable in that problem. We can rearrange and solve in our calculators. And we get that the velocity when it reaches the spring is equal to 11.7 meters per second. So that's the first part of the problem. Anything to add to that?
No, looks good. I mean, I guess that is the speed, 11.7 meters per second. But, you know, something to always remember is that if we're saying velocity as a vector, we have to make sure we say 11.7 meters per second downward, which we have defined downwards as our negative direction. So we go in a negative 11.7 meters per second.
Right. So as it's moving down, it has a negative velocity. Okay. So the second part of the problem asks, what is the maximum distance that the spring is compressed? So how compressed is the spring? So to look at that, I would assume that we need to look at spring energy. So when the spring is compressed, do we have any kinetic energy left?
When it is fully compressed?
When it's fully compressed.
No, we do not have any kinetic energy when it's fully compressed because we're assuming that's the instant right before the spring starts to decompress, I guess. And so it has stopped for a moment, similar to when you throw a ball in the air and right before gravity starts pulling it back down, it stopped at the top for a second.
Right. So we don't have kinetic. Do we have potential energy at that point?
Yes, you still have potential energy from gravity because the spring can't be compressed to 0. That would be pretty impossible. But it still is located at some height above the ground, but it's some height between 1 meter and 0 meters, however far the spring compresses.
Okay, so if we are going off the fact that we have spring potential energy and we have regular gravitational potential energy, but no kinetic, then we can say that PE gravitational plus potential energy elastic is equal to, again, 392 joules, because energy is not created or destroyed, so it must be equal to the total energy. So that gives us mgh plus 1/2 kx squared, which is our equation for elastic potential energy, is equal to 392. Can you see a problem with this, why we wouldn't be able to solve it necessarily?
Well, we currently have the equation for the energy of a spring in compression. We have that in terms of x. And then we have the potential energy from gravity in terms of h. And those are, while they are both distances, they are a very different, they represent a very different thing. We need to figure out a way to express this in terms that we can combine.
Right, because we have h and we have x, we have two different variables, but we can figure out a way of expressing that in which we can express x as h or vice versa. So looking at this, I know that whatever height it's at is going to be equal to the natural length of the spring minus how much it's compressed. So I think I can say that h is equal to 1 minus x. So 1 minus the compression. So solving now, I get 500 x squared minus, let's see, 1 minus x, 1 minus x times 49 equals 392. And then
What?
again,
E minus?
Sorry, plus, yeah, that should be a plus sign.
Okay.
Yeah. So rearranging and writing it in terms of my quadratic formula, at 500x squared plus plus 49 minus 49x equals 392. And then, so then I end up with 500x squared minus 49x minus 343 equals 0. So that's my quadratic formula, which is in a form that I can put into the quadratic equation to solve for x. So if we do that, we end up with x equals 0.879. And that would be our compression of the spring, which is what we're solving for in this part of the problem. Okay.
So if x is equal to 0.879, how high would the box be off of the ground?
So as we said that h is equal to 1 minus x, we can as we said that h is equal to 1 minus x, we can subtract 0.879 from 1, which will give us, so using this equation here, we can say that h is equal to 0.121 meters. That's how high off the ground it would be, using our equation of 1 minus x. Okay. Any other questions about that part of the problem before we move on to the third part?
I think we're good. I think we can move on.
Okay. I'm going to clear the screen so I have more space. The final part of the question asks how far, like what the max height is of the box after it is released from the spring. So after it is thrown back upwards. So we have the box, the spring again. How high does it go? So okay, so again, we're looking at this problem. So at its maximum height, does it have potential energy?
Yes.
Does it have kinetic energy?
No, because it has stopped moving.
Right, similar to when you throw a ball in the air and it stops moving at the top, it's not going to have any velocity. So we can say that at its max height, it just has potential. So potential energy, which is equal to mgh, is equal to, again, our value of 392. Because energy is not created or destroyed, it's going to be equal to our total energy again. So we can say that 5 kilograms times 9.80 times the height, which is what we're calculating for, is 392, is equal to 392. And if you put that in a calculator, you get a height of 8 meters. And what do you notice about that value, Josh?
Well, that's the same height that we started with, is it not?
Right. So our final height is the same as our initial height. And why do you think that is?
Well, as we've said several times now, energy is neither created nor destroyed. So it has to reach the exact same height, because how else, or where else would that energy go? Similarly to Professor Garcia's demonstration in class with the swinging wrecking ball, if it gained energy, when he let go of it, it would have come back and hit him. And if it hadn't gained any energy, or if it had lost energy, then it would have not swung as high. So in the same way as that, when it launches from the spring, it has to reach the same height that it initially started at.
Exactly. So that is the final part of the problem. We answered each of the steps, and unless there are any questions on this, yeah.
I have a question. Why, in real life, is this not the way that it works?
So in real life, it's not going to go to exactly the same height because it's losing energy due to other forces like air resistance and drag. So in this case, we're looking at it in an idealistic situation where no outside forces are acting on it except for the spring itself and gravity. But in real life, there are other forces acting on it, but that's not something we're looking at right now for Physics50.
Right. And so which of the formulas would that be? I remember him saying something in class using the work equation that described losses of energy to other things.
I am not entirely sure which formula that is. Do you remember which one it was?
Sure, I can write it out.
Yeah.
We had, I'm using a trackpad, so bear with me. Work is equal to the change in kinetic energy and that is, it's technically plus, but I'll write it as plus and then explain. Because plus, or I guess this is work final. This is the total work done on it in any given instance would be the change in kinetic energy plus the work done by other things. And in the same way in cases, I can't write very well with this trackpad. But the work done by other things will more than likely always be negative. So then that would make us be minus that value, which would then explain why we don't actually, or the kinetic energy would be smaller, or the total change in it. So that would mean that in total it wouldn't end up traveling just as high in our given example, or the wrecking ball wouldn't, or bowling ball, sorry, wouldn't go quite into his space as in class. So, yeah. Do we have any, all right, so we've reached our time in our session where we will take any closing questions on anything we've talked about so far, or anything in the course as far as logistics or anything of that sort. Does anyone have any questions that they wanted to have answered at this time? Okay. Well, as always, we are in class if you have any questions. Again, in the future, I do encourage you guys to ask your questions more. It's pretty quiet today, so I would encourage you guys to try and get as much of these sessions as you can out of them. And the best way to do that is by participating, asking any questions that you have. Or I suppose me and Freya could be doing a fantastic job and you have no questions, but you know, I do feel that some people probably have questions and just aren't asking them. But these are the times to do it. So in the future, please ask your questions. But for now, I think we will call it. Thank you for attending our virtual session. And we hope to see you later.
Yeah, thank you, and see you guys in class this week. Okay, I'm going to stop the meeting now.